Well, thank you very much for the introduction, and I'd like to thank the organizers for inviting me to talk about a very specific use of thermoelectric power generation. At NASA, we have been using thermoelectric power generation for many, many years, and one of the good examples is actually the Voyager spacecraft that is actually approaching its 40 years of operation using a thermoelectric power generator, or RTG, and it's still basically going very strong, just mostly because of that RTG. So there's a big, long history of use of RTGs for NASA spacecraft. And this has been made in a very reliable technology. But as you're going to see today, I'm going to try to talk about the next generation we're working on and the materials that actually challenges that go into those RTGs and what it takes basically to make it that much reliable. So with this, the other example is the Curiosity rover that has been on the surface of Mars for since almost like 5 years now. It's going to be 5 years in August. And we have actually another mission scheduled for 2020 that's going to be using the same multi-mission RTG. We call it for short MMRTG. And the reason it's multi-mission because it's designed for operating in the deep space as well on the surface of a planet because depending on the atmosphere, basically the active material, the thermoelectric materials are actually protected by a cover gas. Today I'm going to talk about essentially trying to take that particular MMRTG and develop the next, retrofit it with new materials and try to make it into a more efficient RTG. The reason why we want to use RTG is very simple. It's once you go beyond Mars, it's just not enough solar intensity to make the use of solar panel a viable option in most cases. So what we want to use is really what we call radioisotope power system. So it could be the thermoelectric converter itself. The conversion part could be either thermoelectrics or different things, dynamic system like Stirling. But the only RTGs that have been flown have actually used thermoelectric power conversion. So schematically, what an RTG is, you can see the diagram up here. Where you get the nuclear heat source, so we're using a plutonium-238, the decay of a plutonium-238. That's an alpha emitter with a half-life of close to 88 years, so you can support very long missions with this. And this is the heat source itself that has been qualified by the US Department of Energy, and it's essentially producing about 250 watts, thermal watts, and we're just using this heat itself converted through a thermoelectric converter into electricity, as well as using some of the waste heat actually to keep the electronics cool in some of the rovers and some of the spacecraft. So that goes both ways. The one thing to mention that's going to be relevant to the discussions coming up is that particular heat source can provide hot surface temperature up to about 1,000 C. So we are dealing really with very high temperature, and that's when sometimes some of the materials challenges are actually arising from. Just schematically, the chairperson actually mentioned the Seebeck coefficient. That's indeed what we used in the power generation in cooling. It's a slightly different effect, but essentially the principle is you apply a delta T across two types of elements. One is p-doped and the other one is n-doped. And you connect them into series, electrically in series and thermally in parallel, and you apply your delta T, you connect it to a load, and essentially that delta T creates a voltage across this, and that's a Seebeck effect where you generate power. The thermoelectric figure of merit is a function of the Seebeck square divided by the electrical resistivity and the thermal conductivity itself. We define a dimensionless thermoelectric figure of merit by applying the temperature, and then ZT is really the thermoelectric dimensionless figure of merit. So typically, all of these are actually coupled, so unfortunately you cannot actually optimize all of this at the same time. So you need to compromise, and essentially that's a cartoon here that shows around the spectrum of insulators, semiconductors, and metals, what is the best sort of a compromise between those three different properties that I just mentioned. So typically we are dealing with heavily doped semiconductors. That's where the best combination of those three different properties is occurring, and that's where you get optimal ZT. In terms of conversion efficiency, that's a Carnot device. So essentially you basically, it's a function of a delta T as well as the materials factor, which is a ZT that I mentioned about. So dealing with the next generation, you need to both optimize ZT and delta T. That's sort of a key to achieve a higher efficiency. State of the art, there's not a single material or set of materials that actually operate all the way to 1,000 degrees C. So sometimes we like actually to grade or segment some of those materials to take advantage of a full delta T. The Voyager, for example, spacecraft is using silicon germanium, these particular two materials, and the MMRTG is using lead telluride based thermoelectric materials. So all of these have actually a limit, both in terms of the thermal stability, but also in terms of achieving long life for those devices. I'm going to touch upon the degradation mechanisms associated with those RTGs, and one of them is, loss of a material, vapor pressure at high temperature, and that somehow limits, the highest temperature you can use it. So when you're dealing with new advanced thermoelectric materials, nanostructuring has been actually around for almost like 20 years now in terms of the thermoelectric materials. And there is two ways that actually you can potentially use this to your advantage. One is basically manipulating the density of states by doing energy filtering and quantum confinement. And by putting all the states near the Fermi level, you can actually potentially increase the Seebeck coefficient. The other way is really to essentially try to reduce the thermal conductivity, and by putting a number of interfaces in the materials, therefore scattering, hopefully preferentially, the phonons versus the electrons that tend to have a larger mean free path. And therefore, overall, you get an increase in the ZT. This has been realized in several systems. This is an example of the bismuth telluride that was prepared by melt spinning. And if you really do this carefully, you can achieve nanodomains within the materials. And you can see that compared to the baseline, there is a significant increase in the ZT of the materials. We've done something similar at JPL with the materials that we are considering for space applications. And the silicon germanium, we use a different approach where we're using, because typically we use actually bulk material. It's difficult to use with the heat fluxes that we're dealing with. You cannot use really thin films or any low dimensional type of structure. So essentially, we are actually aiming at something that's applicable to our type of RTGs, which are bulk materials. So we use a ball milling technique. So if you do this, right, then you can achieve small crystallites on the order of nanometers. And this particular two plots here are showing the P-type and N-type. There's a typo here. I think one should be the N-type. This is N-type. This is a baseline, what's being used in Voyager, for example, with fairly large micron size grains. And you can see the reduction that you can get by doing the nanostructuring through the ball milling. So you get this. And essentially, it's a matter of how much carrier mobility loss you occur during the process. And it turns out if you can actually increase the carrier mobility over the lattice thermoconductivity, then you get an increase in the ZT itself. So typically the ZT in the N-type, even the baseline is higher than the P-type, so we don't see much of a gain by doing nanostructuring on the N-type, but you actually see some substantial gain on the P-type. So specifically for our application, we're going to be running those devices for 20, 40 years. So, and we are running, as I mentioned, we are running at pretty high temperatures. So grain growth is potentially an issue. These gains that have been reported in the literature are true and real. But the problem is, you tend actually, when you operate at 1,000 degrees C, you're going to get grain growth, and then you revert back to a micron-sized grain, which basically reverse your ZT to the original value. So for us, it has been difficult to apply the nanostructured materials, even though, for a short period of time, you can see some gains. This is a challenge for a long time operation. There has been also some work, mostly in the cooling area, which may be more applicable in terms of a nanostructuring, and you can do this, with lower dimensionality or super lattices, different. That's the one I mentioned about the ZT of the bismuth telluride. So there's all kind of things, mostly around room temperature, and these are actually potentially much more applicable to actually make it into an actual device. Because you don't suffer essentially from the grain growth that I just mentioned. So although these were reported, you can tell from almost like 17 years ago, none of that technology or those advances in materials have actually made it yet into an actual device. Beyond the material itself, there's a lot of basically system integration, device integration issues that needs to be resolved in terms of compatibility with the heat fluxes and everything that is still pretty challenging to actually solve. The material, one of the classes of materials that actually we have focused on is the sclerotite materials. So it's a cubic structure, and one of the features is actually it's got two large voids inside the structure that you can actually fill with different rare earth. And that's actually a very powerful tool to tune both the transport properties, both electrical and thermal properties. So if you put a rare earth in this, you end up with basically a semi-metal, which is where we want to be in terms of thermoelectrics anyway, so that's good. And potentially it's got the potential to really scatter the phonons efficiently and reduce the thermal conductivity. And the reason is most of the conduction is actually through the antimony rings in the nitrogen's rings inside the structure. And if you put those rare earth inside, you're actually not perturbating the conduction. And as I mentioned before, if you actually can achieve an increase in the ratio of carrier mobility over the lattice thermal conductivity, then you get a net increase in thermal conductivity. So that's a concept that has been proposed essentially almost like 20 years ago. And overall, the performance of a sclerotite is actually pretty good. The ZT over 1 have been achieved, which is more than state of the art. So this is good. Going backwards here, but so one of the things that is going on in the community is this rattling of the rare earth inside the cage, the voids inside the structure. Is it really generating all that decrease in thermal conductivity? And we see that decrease in thermal conductivity. This is the unfilled sclerotite. This one is cobalt triantimonide. If you do the rare earth filling, essentially you get substantial decrease in the thermal conductivity. And if you look at the rattling amplitude of the cerium, the rare earth inside those materials, then you can see that you see the temperature dependence that is actually pretty high. So that's the cerium side are highly disordered, and they contribute definitely to the reduction of thermal conductivity that we are seeing. One of the challenges in analyzing this kind of a decrease is once you do this, as I mentioned, you get actually semi-metals. So a lot of charge carriers, and you can get a lot of electron phonon scattering at the same times. So if you do unfilled sclerotides and you just do straight doping, not really filling, so the charge carriers are actually coming from doping, not from the fillers. And you can see that pretty much, if you achieve the same type of carrier concentration, 10 to the 21, you can actually achieve about the same reduction in thermal conductivity. So it's still kind of an open question whether the rattling itself is the only mechanism that yields that lower thermal conductivity, or really the charge carrier phonon scattering is also contributing. But the JPL results on this seems to indicate that's definitely also contributing quite a bit. One of the things you need to worry about by using those materials in space, they're going to be exposed to the radiation, the self radiation from the RTG itself. And also, depending where you go, for example, if you go for a Europa mission, there is a lot of radiation. The radiation environment is pretty stringent. So one of the things you need to worry about over time is how much that radiation potentially can create defects inside the lattice of the materials and essentially change the transport properties to a point that they won't be performing. So typically when we develop those new materials, we actually do a neutron irradiation test to test what would happen. And you can do this by defining the level. So we did that particular test was done to account for basically the self-radiation over a 17 years mission, as well as reaching the mission to Europa, so being exposed for a shorter period of time in the Europa environment. So you calculate the flux, neutron flux, and then you can actually do this in the reactor and measure essentially the properties before and after and see if any defects have been created to actually change the transport properties. So you can see the most sensitive property would be the thermal conductivity, and we typically do this at room temperature, so there's no self-healing potentially of a defect. So this is kind of a worst case. If you actually do this at high temperature, you can get help if you're creating some defects from self-healing at high temperature. But you can see that within sort of a measurement certainty, we don't see any change, which has been the case for all the thermoelectric materials in the past for the type of flux that we expect or the irradiation environment. But essentially, that was needed to verify. So the sclerotides actually are doing good for this. This is the P-types, so same conclusion here. One thing which is important, very important, I'm going to touch upon, is mechanical properties. Those things are not going to be seeing a lot of thermal cycles, but large delta T's are going to be applied across those materials. So they need to actually withstand some of the stress associated with potentially CT mismatch and other type of things. So in general, the sclerotides are actually doing fairly well. They are actually brittle ceramics, so they do better in compression than in tension. So that's when you design your material and your couple, you need to make sure that eventually they're going to be in compression, not in tension. And essentially, the materials are actually doing better in terms of mechanical properties. The sclerotides are better than the laterite and the silicon germanium. So what we are trying to do is actually retrofit the MMRTG and substituting those laterite couples by new sclerotide couples, but changing essentially the envelope of the MMRTG is remaining the same. So this is a very simple, at least conceptually, substitution that we are trying to do. So in that particular RTGs, there is like 768 couples. They are arranged in arrays of different 48 couple modules, 16 of them. And so we are trying to develop all that technology here all the way to the 48 couple module, which is a building block of the RTG. This is kind of schematically, we go from round to square for the sclerotide, but this is essentially just for easiness of manufacturing, the way the materials are actually prepared. There is nothing special about it. You can go from a circular to a square materials. So the gain in efficiency that you can get from this, essentially by using the sclerotide materials as opposed to the laterite, you get an increase of about 10% in conversion efficiency. You can also run them at higher temperature, and that boost in delta T results in another additional 14% increase in conversion efficiency for a total increase at the beginning of life about 24% in efficiency. Oops. So when you're looking at this in terms of the power output of a generator, this is where the MMRTG, and you get some different conditions. This is fuel inventory, how much plutonium-238 is generating, and sort of the load conditions and the environment, the fin root temperature. Essentially, this is how much the MMRTG would put out in terms of the power. The sclerotide system for equivalent conditions would actually be right there at the beginning of life. This is about 25% at the beginning of life. And we estimate that it actually can generate 50% more power at the end of a 14-year mission with a 3-year storage. So that's 17 years total. So this is a big deal. For us, that 25%, and especially the 50%, when is actually the power is needed, when the mission is actually being implemented, and you can actually do more science, and you can get actually lower mass from your system. So that's a very big deal. So we are in the process of actually implementing a technology transfer, working with industry to go from basically transferring the basic materials that have been developed at JPL to developing the older technology. And you can tell that this is taking time. This is nominally a 5-year program where we're going to take it only to a 48-couple module. And then if we are successful in going for all those gates, then we can actually work with the Department of Energy maybe for another 4 or 5 years before we get an actual eMMRTG out of the system. So the development cycles are very long. And one of the reasons is we do all the live performance prediction, live testing, and making sure that everything is validated and we understand clearly how much power and what's the degradation over time. So far with industry, it's been able to basically make the materials, make what we call those metallized pucks, which are actually the scalodites that are actually metallized prior to couple bonding, and making them into p-n couples. One of the things we want to really achieve is low contact resistance between that metallization of the scalodites and the interconnect here. So that typically the goal is 15 microns centimeter square. That shows we are there consistently, and that's no longer an issue. So I mentioned about thermomechanical stress associated with those large delta T's. That's something that we are tracking closely and doing FE analysis to understand the different options in terms of metallization, interconnects, and configuration of a couple are going to yield the best conditions in terms of a stress for the couples. And that has actually to do with, like I said, putting the materials mostly in compression, the scalodite, not in tension, which is actually weaker, much weaker in tension. The couples themselves have been actually generating the power we were expecting. We have a lot of tests on those couples. One of the things in the module is using thermal bulk insulation, and we're actually using a silica-based aerogel for this, which we cast around the couples. This is a sample of a building block of a 48-couple module. And the aerogel itself is not only used as a bulk insulation to maximize the thermal efficiency of the generator itself, but also to reduce the sublimation, the vaporization of the materials near the hot side of the elements, the scalodite elements, which will happen, but we just need to control it to an acceptable level. So we have started some live testing. You can see that we are about a year in vacuum and about a couple of months in argon. This is one of the tests. But the point of this slide is really to show that, well, these things have been working for 40 years in space. So how do you go from basically doing a couple of years of testing maximum to really try to see what's going to happen at 17 years and more? So what we use is a physics-based model when we track the different degradation, quantify the degradation mechanisms, which is the sublimation of the materials, the interface properties of a couple, the change of the T properties of the scalodite materials themselves, and the insulation. So these are the 4 key degradation mechanisms that could affect the performance of the RTG over time. So you test for a couple of years. You do this under nominal and accelerated thermal conditions, which is the beauty of thermoelectrics. You can actually increase the temperature to accelerate the degradation mechanisms, but just you need to confirm this is just an acceleration. You're not introducing new degradation mechanisms, but by doing this acceleration and quantifying that acceleration, you can actually model that degradation mechanisms and extrapolate over the life of a generator. So we do also, we're looking at this from a reliability point of view and statistical point of view. And so we have a whole model to do that. So far, we've been testing the scalodite properties for over 2 years. And what we see is that if anything at all, the ZT is increasing after 2 years of testing versus compared to the baseline materials, both for the N and P type. So that's not an issue. The materials are actually very stable up to 650 C. Sublimation rate, again, we're using our gel to really capture the control the sublimation, and we have achieved actually sublimation rates which are consistent with the rates that we need to achieve our degradation rate, our performance goal for the 17 years of operation. So this is more like, looking at the reliability approach, where we actually looking at the different degradation mechanisms. We look at defining density functions for all those parameters and combine this into life performance prediction using a life performance prediction model. So the next one is going through this, but I think I'm going to skip this in the interest of time and just wrap up So we're always on the lookout for advanced thermoelectric materials. So this is a great deal for us in terms of improving the efficiency of the RTGs. This is really enabling for potentially a number of missions. Nanostructuring has its own challenges for our application because we're operating at high temperature. So unless you find a way to sort of control the grain growth, then that's potentially an issue. And we are in the process of trying to retrofit the MMRTG with a scutellite-based technology, and so it's well on the way. And we're hoping that we're going to demonstrate that RTG. Scutellites are also used for many different terrestrial applications. This is being developed for automotive waste heat recovery and residential waste heat recovery. With this, I'd like to thank you for your attention, and I'll take any questions if there is any. Thank you.